next speaker, and I have the pleasure to invite on stage my friend and colleague, Professor Doug Hooton from the University of Toronto.
Thanks very much, Nicola. It's my pleasure to be here in Chennai. My first trip to India, and it's quite a pleasure to see what's going on. It's very impressive what's going on here. My talk's going to be a bit different. I'm going to talk about performance specifications, which is a bit different. So I'm not going to talk about research work or specific details, but the issue of how you try and attain performance in construction. Okay, so what is a performance spec? What are the roles and responsibilities involved with that? What type of tests and when do you test? The need for inspection, and I'll give hopefully an example of that. And just to mention, the Rilem had a TC 230 on performance-based specifications that came out, the report came out last year, 2016. So you might find, if you like this or find this interesting, there's a lot of information, and some of what I'll be speaking about is it contained in that document, the TC 230 document. Okay. And the reason I got involved in this is because mainly certainly from the North American perspective, there's been a big interest in moving from traditional prescriptive specifications to performance specifications. And what we found by doing a review of the international literature is that there are not a lot of performance specifications. People talk about performance specifications, but in the end, they're just not performance specifications. And typically prescriptive specifications in various, and I'm sure India has them, every country has developed their own historical specifications from local experience. And you put limits on various parts of the concrete or mixture designs or materials to obtain durability in various exposures. But they don't necessarily address all the owner's desired performance objectives, especially when you think about crack control and other issues that influence durability. They're very often not specified issues that will address minimization of cracking. And the other thing about prescriptive specifications, they limit innovation. There's a lot of changes in concrete materials, in the admixtures, the different cementing materials, that traditional prescriptive specifications discourage their use or make them impossible to use in some cases. So it's not helpful. The other interesting thing about when you talk about prescriptive specifications is they often prescribe in great detail what the concrete has to contain, but then we call them performance implied specifications. But the performance requirements are kept a secret. They're not written down. They're not communicated to the contractor before the work started. They're only communicated when the owner or the specifier is unhappy with the result of the concrete. Things like shrinkage cracking, curling, scaling, creep, excessive deflections, things that are, or color uniformity, things that were not specified, but not communicated in advance. So the objectives were not communicated with these things. And often with a prescriptive specification, it's difficult to avoid some of these problems. And you can end up with unintended performance. There's some examples here. Plastic shrinkage cracking, because somebody didn't take care of the issues for that, the conditions that would lead to plastic shrinkage cracking. On the right-hand side, there's tearing of a bridge deck surface, a brand new bridge deck with high-performance concrete, but it was with the weather and the certain admixture combinations, there was premature slump loss, and the finishing machine tore the surface of the concrete, and that surface has been ground away, but the cracks extended quite deep. Or using a concrete with insufficient workability for the application, that's shown in the lower left there, with a big void under the rebar because the concrete wasn't compacted in around the rebars because it was just too stiff for the application with the machinery and equipment that were available. And sometimes you get unintended performance due to prescriptive requirements on mixed designs. The one on the right there is the underside of transverse cracking on the underside of a bridge deck that's less than a month old, and it's raining and the water's leaking through before the waterproofing membrane went on top of the bridge deck because of prescriptive specifications on the size of the aggregate they could use, the cement content, the types of cementing materials that the owner put on there resulted in increased thermal cracking on that bridge deck. And on the left, there's another one where you've got a mass concrete tunnel in a transit station where the owner put limits on the maximum amount of supplementary cementing materials that could be used, and the concrete got too hot, and they got excessive thermal gradients that resulted in cracking, and it's below the water table and they're leaking. This structure isn't even open yet, and it doesn't look very good, and it's supposed to last 100 years. And there's a whole bunch of things you can do. Thermal cracking is something that has become a bigger issue, and this Oscar Onomatai from Kiewit Construction, big contractor in North America, has developed thermal control plans, which is quite detailed, to try and limit this thermal cracking, because it's a big issue that hasn't been dealt with very well. It's not covered in specifications very well, so the contractor in this case is doing it to prevent problems so they don't get unintended consequences on the site. So they want to control the placing temperature, the maximum temperature. They want to control the thermal gradient in order and there's a bunch of things they do, not just the mix design, but how they place the concrete, placing sequences, heat removal, form removal, insulation on the forms, and duration of that protective measures to try and minimize the cracking. Okay. So if you're going to specify durable concrete, design is more than selection of the concrete materials, and that's the big problem with prescriptive specifications that say you have to use a certain water cement ratio, a certain cement content, certain types of cementing materials, is that doesn't address the objectives necessarily. The owner's objectives need to be specified clearly. The designer who works for the owner should be getting from the owner what they really want from that structure, and they need to define the exposure conditions for various parts of the structure that are going to be exposed to different environments. Like foundations are going to be different than structural elements above grade. They need to think about all these things like temperature control, adequate compaction, protection of fresh concrete, curing. All that stuff needs to be detailed in the spec and has to be inspected to make sure that it's being actually carried out. There's no point putting it on paper if you're not going to put adequate inspection in place to make sure that these things are actually happening. And the push to performance and objective-based specifications has been there to improve the chances by detailing these requirements, improving the probability of getting durable concrete and meeting the owner's objectives. Now, I got involved with Ken Hover at Cornell University and a consultant, John Bickley, in Canada, and we did work for the U.S. National Ready Mix Association several years ago on developing several reports on performance-based specifications. The first one was just a review of the international specifications at the time. The second was what we thought needed to go into a performance spec. But then, of course, from the ready mix industry, that was only one part of it, so we then handed that off to the American Concrete Institute, and they formed a new committee, 329, on performance specifications, and adopted basically, with some modifications, our document. And they're now working to try and develop an alternative to the ACI 301 specification that's performance-based, as opposed to the existing prescriptive-based spec. In the Canadian standard, we developed, in 2004, the Canadian standard, we got rid of sort of we moved towards either you had to define a performance option or a prescriptive option for specifying concrete. We used to have a mixed thing where people would specify some things, but other things were performance related. We said, well, look, that confuses everybody. If you don't know what the roles and responsibilities are, the contractor, the concrete supplier, and the designer, then everything gets confused and it makes it more difficult to achieve things. So we said, look, performance requirements apply when the owner requires the concrete supplier to assume responsibility for the performance of the concrete as delivered, and the concrete to assume responsibility for the concrete in place. Sounds simple enough. And it's a performance spec is a way of specifying a product where the outcome is given in mandatory language. So in other words, there have to be mandatory requirements, and they have to be measured. So you set performance limits, and you have to have measurable results that can be done with industry standard test methods. And then you leave the contractors and the suppliers alone to do the job to meet those performance requirements. The trick to that is specifying all the performance issues that need to be addressed. So we did this in 2004, and we developed a performance table and a big appendix to explain all the details and roles and responsibilities, and we've modified that in 2009 and 2013. We're currently going in our next code revision in 2018. We're going to detail some more things, because as we do this, we're evolving and learning more about some of the issues related to implementing these performance specifications. And again, there's often more than one way of achieving durability, and there may be a better way out there because there's new materials, you know, it's just environmentally friendly materials, different approaches, different ways of placing concrete, different methods that can be used by the contractor that may result in better performance. So if you set performance limits with proper performance test methods that can be measured, then the contractor can work with the concrete supplier to try and achieve those performance limits, but with a lot of flexibility to do it in the most efficient way. Now, this is not for all concrete. Obviously, if you're doing residential construction or a lot of commercial construction, you can't use this currently the way it is because you don't have enough lead time to do a lot of the pre-qualification testing that's required. And it's really, this is practical for large structures that have lead times of where you need long service life. And we've seen several of these projects where the people are specifying long service life and using performance-related specifications to get what they want. And of course, the key to this thing is defining roles and responsibilities of the various players, which, you know, you have the owner's designer, you've got the contractor, you've got the subcontractors, you've got the concrete supplier. And so, but the key, one of the keys to make that work is the concrete supplier has to work together with the contractor. And a lot of these big long service life projects, typically they work as a team. A contractor will come in with the concrete supplier to figure out how they can bid the job to meet the achieve the performance requirements as a team, because they need to work together, not against each other. And a spec should provide a quality control system for both the owner, the contractor, and the supplier. And so everybody needs to define that. The quality control is typically done by the contractor, and quality assurance testing is done by the owner's representative. And you need good communication, because things do happen that you get deficiencies in achieving some of these things, but they need to be changed quickly as possible. So if there is a deficiency, it's recognized, it's communicated, and it's addressed, and you say, this is what we're going to do differently to prevent it from happening in the future. So there's a lot of communication involved to make a successful product. So this is largely from the Canadian specification, so that we define all these details about responsibility. So the owner or the owner's specifier needs to appoint a competent design authority, who is the specifier, to implement that quality assurance process. You need to establish the performance criteria based on the placing and in-service conditions. You need to make sure the technical specification clearly states the performance criteria and set pre-qualification or verification requirements, and conduct a quality assurance process. And any other thing that, like 7, if they don't want any cracking or they want certain crack limitations on crack widths, and they need to state that as well. And some keys to that, because often what happens with large project or a number of projects is that the contractors bid it based on volumes. They said, we got 5,000 cubic meters of concrete or something like that, and they cost it based on supplying that much concrete, as opposed to reading the specification to find out what the targets are, because they may find that they aren't aware of, or they claim they aren't aware of the special requirements for durability in a performance project. So one of the requirements is to require all bidders to attend a pre-bid meeting where they're told what these special requirements are, so they have to put that into their bid tender. And it includes their subcontractors. They have to detail in their bid how to meet those requirements in their submittals. And the owner has to have this, and the owner's designer has to have the strength to say, look, we're not going to accept a low price bid if it doesn't address these requirements. because then you lead to problems if you don't deal with those things. And we've found as well, if you've got, especially for long service life projects, that you need to have pre-pour meetings. If there's an important pour where there's things have to happen and you need to have the contractor and subcontractors aware of the issues, we've sat down with the concrete suppliers, the subcontractors, the forming people, and said, look, this pour is happening, these are the special conditions, the weather's going to be this, how are you going to address this? Do you have the equipment in place to protect this against things like plastic shrinkage? What are you doing about it? Have you got the equipment and people in place to deal with that thing? And that solves a lot of the problems, as long as everybody's there and they're aware of the problems. And of course, the contractor has responsibility. They've got to be aware, as I mentioned, of the performance requirements prior to bidding, so they can't say, oh, I didn't know about that, or I didn't price that into my bid. And they need to put that into their pricing and detail that. The contractor then has to procure the concrete. The owner doesn't buy the concrete. The owner deals with the contractor buys the concrete. And they need to work with that supplier to get the concrete they need for both the placing conditions. It should be the contractor that sets the workability requirements on a job, not the designer, because the contractor has to place it with the people and equipment he has available to place that concrete properly. And you've got to submit documentation to demonstrate that you've met the performance requirements by pre-qualification testing, which I'll talk about shortly, and be aware of the other things that need to be done, and set up, implement a quality control plan to ensure that owner's requirements will be met over the production of concrete. Now, the concrete supplier has requirements too in a performance specification. They've got to show that their materials meet all the standards, that the mix design meets all the pre-qualification requirements. So they would have to do pre-qualification testing as well to show that the mix will achieve these requirements. If it's a diffusion requirement or a strength requirement or a shrinkage limit, that they have to demonstrate that in advance and have a quality control plan for the supply of concrete, that the concrete's going to be delivered in a uniform manner. And as I mentioned, you need a high degree of coordination between the supplier and the contractor to make that happen so that they work together as a team. Now, one of the things about testing is, when do you test in a performance specification? You can test the concrete, the supplier can test the concrete at pre-qualification testing. Commonly, the most common testing is done at the end of the chute as the truck delivers, assuming it's truck delivery, delivers the concrete. People take samples, they measure the slump, they measure maybe air content or some other properties. And so you get its acceptance at the chute, but what we're really interested in is, if you're doing pre-qualification, you want to identify at the job site that the concrete you pre-qualified is the stuff that actually got delivered, because mistakes get made. And so you need to check the delivery ticket, make sure it's the right mix, but you also want to make sure it's meeting those same properties that were pre-qualified, and that's challenging. Sometimes people are interested in point of placement, because if you're going to pump the concrete, you may knock the air out of it, you may change the workability, so a number of things may change during the placing process. So some people want to test at the point of placement. The owner doesn't care about any of that. The owner cares about the in-place structure. They want a structure that meets their requirements. And so a number of owners have adopted end result specifications where they actually pay the contractor based on testing the in-place concrete. And they'll pay penalties and bonuses. Our highway department in Ontario, Canada, does that, has been doing that since 1998. They have a table. If you achieve the performance requirements, you get 100%. If you fail by a certain amount, they have a percent within limits approach. You get increasing penalties down to about 50% of payment. And if it's really bad, you tear it out. But if you do it, exceed the requirements consistently, you get a bonus. When this first came out, contractors thought it was the worst thing that ever happened to them. Within a year, almost every contractor was getting a bonus. And the highway department was happy because they were getting good, consistent concrete, because contractors are in the business of making money, and if you have a system where they can get a bonus, they'll achieve that bonus because there's an incentive, a carrot and a stick approach. So it's been quite successful in Ontario in reducing the number of failures in the concrete that's supplied to things like bridges and paving structures. Okay. So we want to do pre-qualification testing to make sure that the mixture that's proposed will meet the specification. You want to do some on-site quality assurance to make sure that the materials, the concrete supplied is the same as pre-qualified, as I mentioned, identity testing, and you may want in-place testing, which could be non-destructive or destructive tests, depending on that. So typically, pre-qualification tests would be strength at various ages, because it's not just 28-day strength. Contractors often have construction schedule issues based on when they can strip the forms, when they can remove reshoring on suspended slabs, and so they have other requirements besides the specified strength that the owner specifies. Workability issues. So if it's a durability issues, you need some sort of a permeability index or penetration-related index to predict durability, drying shrinkage measurements, etc., temperature rise characteristics. So those are things that could be evaluated. Now, for a permeability test, people have talked about ASTM 1202, the Coulomb test. Not a great test, but it's standard and people know how to use it. We're looking at replacing that currently at ASTM with a bulk resistivity method that is much faster and more efficient. Some European groups have used this NT build rapid migration test that's shown there, the NT 492. You need something that's relatively rapid that you can check this on site, because these tests are used during the quality control process. They're not pre-qualification tests, they're checks on acceptance. Now, the big problem with acceptance testing is time constraints. So we need those identity tests to confirm that the concrete is being delivered. So when the concrete arrives on site, you would like to have a DNA test to show that the pre-qualified concrete is the concrete that's being delivered, but we don't have a lot of test methods. Typically, we have people do slump or slump flow if it's SCC concrete. They may take the temperature of the concrete, which that affects things like slump loss at high temperatures with admixture slump loss. Of course, if you're worried about freezing and thawing, you do an air meter test. But even a density test can look at uniformity as well, act as a uniformity thing, just measuring the fresh density of the concrete. The other one that's interesting is the microwave test, which can be done on fresh concrete. It's not perfect, but in about 20 minutes you can determine the water content of the concrete, because the biggest variable in delivered concrete is the water content, because there's water in the drum of the concrete before it gets filled with concrete. After they put the prescribed amount of water in the concrete, the truck driver washes down the chute quite a bit, depending on how he feels and how much time he wants to spend, and extra water gets added. And of course, on site, other water can be added, but at least when the concrete's delivered, you want to know if the water content exceeds the water content, which would then indicate rapidly that quickly that concrete's going to be a problem before you wait for 28 days to find out the strength is low or the permeability is too high. So you can estimate water cement ratio to about 0.05, assuming that the cement content is constant. But usually the big variable in mixed designs is the water content. You can assume that most things are pretty accurately predicted because of the requirements of quality assurance for how accurate the scales are for aggregates and cementitious materials and admixtures. The New York Port Authority used that on all their projects. At JFK Airport, they used it on every delivery for their paving structures. They used it in the Freedom Tower on the delivery. I was out in the Freedom Tower site, and they had microwave ovens, and each truck had to wait until they got the microwave water content in addition to all the other testing before that concrete got pumped up into the structure, because they wanted uniform quality concrete that would meet their requirements. Of course, we'd like an instant test. 20 minutes is a long time, and if you wear a plaid shirt and have a helmet and you can sniff the concrete, this is what we would like, but maybe not soon. One of the things about setting performance limits is you will have to allow for the variability. All test methods have variability. They're not uniform. They don't give you a single value. There's variability in test methods, and you have to allow for that. And we typically allow that for that because most people would design for a strength higher than the specified strength, some target value plus the standard deviation of the production, and say that's 15% higher than the target strength, or the specified strength. And of course, if things are low, you don't throw away all the concrete. If one cylinder or cube is tested low, there's statistical evaluation of cores based on running averages, and you would accept concrete that in an occasion that's less than the specified strength, because you know that some of that is due to the variability of the test method. And we do that in our Canadian spec for air content, air void spacing, but not so much interest in India because you don't have the freezing issues we do in Canada. But we do that for the rapid chloride permeability specification. For one of our exposure classes, which would be a normal parking or bridge deck, not high performance, we require 1,500 coulombs at 56 days. So a producer would target some value lower than that so that they can achieve the 1,500, and our limit actually says that the average, the running average of 3 has to be less than 1,500, with no single value less than 1750, greater than 1750, because we know there's variability in the test result. So you're not going to penalize them for having an odd test result that exceeds the limit. You have to realize there's going to be that as long as the average stays below the limit. And of course, you need to do proper inspection, because if you don't inspect, you're not going to get what you want. And that means inspecting before the construction. One of the biggest problems I see is cover depth. Nobody measures cover depth beforehand, or very few times, and that's where your biggest opportunity to extend service life is, making sure you have the achieved cover before you place the concrete around the bars. And you want to make sure that all the tools are in place for compaction and curing. You want to make sure that the delivery of the concrete is being tested as it arrives, and you want to make sure that the concrete is protected against plastic shrinkage and curing is started on time. That's relevant for the service life exposure. So inspection involves a whole bunch of things, but often it doesn't exist except for taking cylinders and measuring slump at the job site. And so lack of cover control is a huge problem. This is some data from the 1980s from bridge columns in the UK. It shows that the average depth of cover on a series of bridge columns was 30 millimeters, but it varied. The standard deviation was 13 millimeters, which means some of them were less than 10 millimeters. And some of them were up to 60 millimeters. So you have this huge variation, which means if we're talking about the service life prediction, time to corrosion, well, the depth of cover is huge in that prediction. And so you're going to start to have corrosion very quickly with the ones that are at the low. When we did the latest parking deck at the airport in Toronto, which I was involved with, we did pre-cover depth checking before they were allowed to place the concrete. And if the cover wasn't right, we made them correct that, push the bars down in. And so we ended up achieving, the specification was 40 millimeters. We actually achieved 50 on average with a standard deviation of 3 millimeters by checking that with the gauge before they placed the concrete, which means that the reduced variability will increase the chance of getting durable concrete over a long time without corrosion. So you can minimize that variability, which can add decades to the durability of concrete. Okay, I'm seeing I'm right out of time. We've done this in some projects and transit stations, and where we have defined owners' objectives. I worked with John Bickley a few years ago to design this particular one, amongst others. And the problem they had is they had an underground transit station. They had water that was below the water table. They were going to have leakage. They were worried about cracking and joint openings, so that was the primary objective. We wanted a concrete that was watertight. So we didn't tell them how to make concrete. We set temperature limits, temperature differential limits, shrinkage limits, and we let them we said, look, the transit station is not going to open for a year, so why specify 28-day strengths? So we specified 91-day strengths. And we set diffusion limits to prevent long-term ingresses because there were some chlorides in the groundwater. So we let them come up with innovative ways of achieving that without cracking. And we gave them some commentary on how they might achieve that. They should minimize the heat of hydration. They should use high volume SCM replacements. They should control the delivery temperature of concrete, because that's a huge factor in the heat that's generated. They should consider insulated formwork and extending formwork removal times to minimize temperature gradients. So we provided that commentary, but the spec didn't do that. And what we made them do, and a lot of performance specs that now in Canada have done this, we require monolith testing. Here we use cubic meter tests, insulated cubic meters to simulate the mass concrete, and the suppliers do this in advance. And this is a picture on the left, shows several blocks of different mix designs. They cast cubic meters with thermocouples in place. We look at differential temperatures and maximum temperatures for the different mixes that are being pre-qualified. And then the contractor and the supplier can core that thing and get actual in-place strength. When you look at high volume SEMs and you're casting a cylinder that's 150 by 300 or 100 by 200, That concrete strength has nothing to do with the strength you're going to get in a structure, because they're very thermally sensitive SCMs, fly ash and slag. And so if the temperature goes up due to the thermal mass, you're going to get much higher strengths at early age than is predicted by small laboratory specimens. So we actually make them do the testing on the blocks where they'll see the benefit of that. And so we get the thermal performance. You can look at maximum temperatures, you can look at the gradients, and see if it meets the performance specifications. So we've done that on several jobs. A number of the contractors even built bigger elements now and do the same thing for more complex elements to achieve that. And we've done that with there's some big pours, 2.2 meter slabs at this transit station, and we actually achieved the limits they had. We had a 55-degree maximum limit, a 20-degree gradient, and they had thermocouples throughout the slab, and they generally achieved that in the weather. Of course, it was cool weather. But if you don't do that, you can get, as I mentioned before, thermal cracking where the owner put prescriptive constraints. So, performance specifications can result in better concrete and durability if everybody's part of the process and everybody knows their roles and responsibilities. It allows for innovation, flexibility in materials supply, innovation in the way concrete's placed and taken care of. But it means more than acceptance of concrete at the end of the truck chute. And to an owner, it means in-place performance of the structures. The contractor and producer and concrete producer need to work as a team to meet those objectives. There is a learning curve because if nobody's done it before, they need to learn. But now, certainly our spec's been out for 13 years now, people are getting on to the concept and about how to deal with this thing. And we're trying to make it easy for them by modifying the specification. But lastly, we always need better performance tests to cover all these things. It's not perfect, but you can't wait for perfect test methods to start the process. If you create the process, test methods will come along to address those issues. So thanks very much. Appreciate your time.
Thank you very much, Doug, for this presentation.